As device gate length gets shortened, there is a unwanted effect occurred. A short channel effect, first of all, punch through. There is a unwanted drain to source leakage on not depending on gate voltage, which was caused by a depletion overlap on substrate, and the punch through made it poor substrate shear swing, which means a poor on-off ratio, and also a threshold VT roll-off, which means a threshold voltage gets rolled off as drain voltage gets higher. So the off voltage and on voltage gets different between depended on drain voltage. So as same device, the threshold voltage get differentiated. And there is a Deber and Gider. The Deber is a drain-induced barrier lowering. So the gate, not depending on gate coupling, as drain voltage gets higher, then the drain source to drain leakage appears, which means a poor gate coupling. And also there is a Gider, which is gate-induced drain leakage. This occurs when gate bias gets negative voltage, which means accumulations on MOSFET structure. So to solution to this short channel effect was a LDD, which means lightly doped drain. Lightly doped drain makes lower electric field to the junctions, and also a pocket implant. Pocket implant is by implanting a lightly doped P-type substrate between junctions that prevents the punch through. We can think about this problem as effective resistance in the device. There is a very many parasitic resistance in the MOSFET, and those effective resistance hard to measure separately or independently. These resistance are lowered by solutions like LDD or hollow implant. However, the contact resistance is very problematic. To reduce this contact resistance, the contact resistance is occurs because of there is another diode on the contact, which means there is a metal semiconductor junctions on the contact. To solve this problem, we used a heavily doped contact semiconductor, so that we can use tunneling effect. And there is another problem, a hot carrier effect. The hot carrier effect means that on high VDS, so drain to source voltage situations, which means a high electric field on drain to source, then there is a lot of electrons collide between lattice during the electrons go through the channel, which means there is a higher energy, and these energies collide with lattice and they make unwanted ionized electrons. So that the situations appears like a diode's breakdown situation. And also, because of this hard carrier effect, also velocity gets electron velocities are saturated. And there is another problem is latch up. In MOSFET, source and drain are negative N plus doped and substrate is positively doped. We can say those structures are effectively NPN bipolar junction transistors. Those latch-ups are hazard to the logic device because there is another logic gate right under the MOSFET. To solve this hazard, we use locus, which means it's a local oxidation. There is in CMOS, there is two MOSFETs, and between these two MOSFETs, locus implants the thick oxide barrier between them, so that they can lower this leakage. However, locus is not covering below the under the substrate, so there is a leakage between them, between the bulk MOSFETs. So there's another solution, DTI, deep trench implant oxide. So it completely blocks between the leakage. The locus was first produced, and as this implant technology gets easier, so then the DTI process came out. So to solutions to this all effect of short channel effect, we use a high K dielectric material. Using a high K dielectric material and thick insulator, we can reduce the jitter as a gate leakage and electrons trapped in a gate barrier. So using this thick oxide, there is no leakage to the gate, and using high K material, we can relaxate this inner trap. And there is another solutions, is a FDSY, which means fully depleted silicon on insulator. Like as we said on punch through, the same process, the FDSY is good on swing and low debor, because the channel is very fully depleted at equilibrium state, so there cannot be a leakage. However, there is, as the cross-sectional area between the source drain are very small, so it has a bad conductance, which means bad effective resistance, high effective resistance. So to get a better gate control or coupling, we use three-dimensional structures. Three-dimensional structures has the advantage that giving more cross-sectional area to the gate, so that they FinFET like GAA, like three-dimensional devices can have more gate control because of the more cross-sectional area. Also, GAA is that gate all around MOSFET, which means in 3D FinFET is that has coverage of three sides, like FinFET like shaped like here, and there is a substrate and lightly very thin oxide layer, and there is a gate. So FinFET covers a three side, 1, 2, 3, and GAA gate-all-around device covers more area than the FinFET. Four side. There is a source and drain. Between them, the gates are covered like this, and there is a oxide between the substrate. There is source, drain, gate. And also we use a 3-5 material. 3-5 materials has super lattice structure, which means 3-5 materials. This is like MOSFET structures, but there's a lot of layers with different hetero structure. By using superlattice structures and not using dielectric, 3-5 materials use a quantum well effect, and also 3-5 materials have very high mobility. So 3-5 devices are used for a high performance device, because high mobility means that electrons can move faster, and which means that it has faster response time. And there is another type of FET, field effect transistors, is JFET, junction field effect transistors. JFET uses a depletion to control channel. Like 3-5 material, it has no dielectric. And there is a MESFET. MESFET is a combination of JFET and 3-5 material. It can drive very large current compared to planar MOSFET or GAA 3-5. So MESFETs are used to power device. So JFET uses a depletion, which means there's no dielectric and source, drain, gate. If we give a gate to reverse bias, then the depletion width would be narrow, wide. So the channel gets narrowed. And there is a BJT, which means bipolar junctions transistors. The applications are similar as FET. It is just a switch using a electron hole pair. Field effect transistors was unipolar device, which means that it uses channel as a hole or electron as one carrier. MOSFET strains are similar to collector to BJT, gate to base, source to emitter. There is 3 modes between on BJT. There is a cutoff, active, and voltage saturation. And emitter-based junctions, at cutoff, the emitter-based junctions and collector-based junctions are both reverse biased. So there is no current flow between emitter to current. So we say cutoff. The cutoff mode used in logical device is logical low signal, and active mode at active mode, emitter-based junctions are forward biased, and collector-based junctions are reverse biased. So at active mode, the current flow, the input current flow is a current to base, and the output current is current to collector. So by giving to base to small signal, small current, the collector current responds to more very large scale output current. So on active mode, we use this as an amplifier. And there is a voltage saturation mode. At voltage saturation mode, emitter-based junctions and collector-based junctions are both forward biased, which uses a logical high. At saturations, there is a voltages are limited to the limited. There is a very important effect, which is Miller effect. If you try to use a BJTs or OP amp, like here, is input voltage and output voltage. So from the input, the load impedance gets high amount as the amplifier's gain. So, which means there is a more higher impedance. The higher impedance is related to response time, tau, on RC circuit. And as impedance gets higher, then the frequencies would get lower, which means there is a poor frequency response. And that means there is a band limited between input and output gain. And there is a significant parameter on BJT is alpha, which means common base current gain. The common means that we're gonna ground the base. So alpha can be expressed as like here, ratio between input and output. In here, input is emitter and output is collector current. The alpha is consisted with gamma, inject efficiency, and alpha T, and transport efficiency, and M, collect efficiency. So first, inject efficiency is consisted with INE and IPE over INE. IPE means that whole movement at emitter. As the property of BJT was that the carrier was not unipolar. So in emitter, there is two movement here. At active mode, the barrier will go lower and the electrons will be injected. Also, at base, the holes would be injected to the emitter. So to get more efficiency, then we need to be more difference between concentration. Like We have to dope higher than the dope higher at emitter than the base. And there is alpha T, transport efficiency. Transport efficiencies are consistent with I recombination over INE. The recombination current at base is proportional to the expected value in injected carriers, and INE is injected current at base. To make we want to be alpha T to be low recombination as possible and injected current more injected current as possible. To make more efficient, we have to make base thin as possible. And lastly, there is a collection current. At base, the injected current electrons diffused through base to collector. And also, there is a hole in the collector gets through to the base. So to make more efficiency, we have to give more bias, reverse bias between collector and base, and we have to make more difference between collector and base junction. Collectors get more highly doped, and base gets lightly doped. And there is a beta, which is common common emitter gain. The betas can be calculated using KCL, which means a Kirchhoff current law, and continuity equation. In real device, these solutions has limitations because of if we degenerately dope the emitter and collectors, then there is band gap narrowing happens. The effect of band gap narrowing has a effective band gap narrowing makes the barrier between emitter and base large. So the electrons cannot hard to diffuse from the emitter to collector. To solution, we use this graded doping technique. We call it a drift transistor. At emitter-based junctions, we relatively highly dope base, and the collector-based junction, we relatively lightly dope at base. So like graded doping, we give a gradient to the base. So by using technique at active mode, electrons diffuse through emitter to base, and after electrons diffuse, also at base junction, base region, electrons would be diffused, and by this potential difference, electrons get diffused to collector more fast. So the carrier lifetime would be shortened. The diffusion length, diffusion time would be get shortened, and there will be a low recombination current. And there is another graded doping giving a difference of potentials is that hetero injection. At emitter-based junctions, we dope a silicon only, and collector-based junctions will dope germanium more more as through the emitter-based junctions to collector-based junctions, which affect same way as graded doping.